This unit is going to be all about oscillation and waves. So we're going to start with things that can oscillate. Now, oscillate just means moving back and forth on a repetitive path. So for example, if we take this block, we pull it down, so normally you see where that dotted line is. That's kind of the normal resting position right there at that dotted line, right there. If I pull it down and I stretch it downward with some value, and I let go, it oscillates up and down. This is oscillation. Notice how it keeps going forever. If I add friction, it eventually slows down and comes to a stop. The other example we're going to see of oscillation is a pendulum. If I pull this thing back, maybe 15 degrees, and I let go, it swings back and forth along the same path. Again, that's called oscillation. When there's no friction, we see it just continues back and forth forever. And if I add friction, it'll come to rest. So the first thing worth noting is when I pull this thing down, right? And let's pause the video. When I pull this down, the spring is stretched out. So what happens when you stretch a spring? It's kind of like a rope. The spring is getting pulled back upwards. This edge right here, the end of the spring, is pulling itself up. Like the rest of the spring, it's like kind of like a rubber band. So this end gets pulled upward, back towards the normal relaxed length. And when this thing oscillates upward, when the displacement is like that, what's the spring doing? It's pushing the block back down. How about the pendulum? Well, when the pendulum swings out to the left side, gravity, its weight, is going to tend to pull it back toward the middle. And when it swings over to the right, again, its weight, its gravity, is going to tend to pull it back in toward the center. So what do we notice? Both systems feel this restoring force. This guy, whenever you push it up, the force pulls it down. Whenever it gets pushed, whenever it displaces down, the force pushes it back up. This one too. Whenever you displace it to the right, the force pulls it back to the left, toward the center. Whenever you displace it to the left, the force pulls it again back toward the center. So back to the right, the other way. These are the two scenarios which illustrate simple harmonic motion. Let's draw that frictionless mass spring system. And we're going to make it horizontal instead of vertical. So you can imagine here's the spring. It's stretched out. Here it is. It goes back to the middle. And then it compresses. And that cycle repeats. It starts here, it goes in, back out, and just continues going back in and out and in and out. The mass is m, the stiffness or spring constant is k. What is the restoring force that pulls this block back in, pulls the system back toward the middle? I mean, here's the normal place where it just rests. We call that, by the way, the normal resting location, we call that equilibrium. And that's a term we're used to. We're familiar with this. When you pull the thing and displace it to the right, some amount x, the spring generates a force the other way. And when you displace it to the left, the spring generates a force in the opposite direction. And check it out. You see how that spring points back to the middle? whether, it doesn't matter where the thing is. The spring is a restoring force, the spring force. It restores the system back to equilibrium. There's an equation that tells us how to calculate that spring force. The equation says the spring force is negative the spring constant times x, the displacement. So why is there a negative? Well, think about it like this. K is always some positive number, maybe it's 5. If your displacement is positive 4, then look at this. The spring force comes out leftward, negative. Right? If your displacement is positive, the spring force is negative to the left. And we could instead, say, well, what if the block gets pushed over to, what if the block is displaced to the left? Well, if you have a leftward displacement, then you have negative and negative, that makes positive 15. So a leftward, a negative displacement, would create a positive force. So the negative sign, the negative sign here just means F spring and X are always in opposite directions. Okay. This spring, let's go back to the animation. There we go. Start it back up. As the spring oscillates up and down, there's a repeating cycle. So I could get my stopwatch out. And I could measure how long this cycle lasts. Well, what is a full cycle? It actually doesn't matter. You can start the cycle at the bottom, right? Pause it right here at the bottom. Let it go all the way up and back down, and that's one cycle. That cycle repeats. Or if you want, you could start somewhere else in the cycle. You could start at the top. Let's try that again. You could start at the top, let the block fall all the way down, return back to where it started, and that would be one cycle too. But I like to start at the bottom. Here we go. Alright, and I'm going to go ahead and hit play or start on my stopwatch. And here we go. I'm going to measure how long it takes to go all the way back up and then all the way down. And stop. So 0.67 seconds. That's the time to make one oscillation. We call that, wait, we already know that term, that's the period. The period in this scenario still capital T, is the time to complete one oscillation, one cycle, one back and forth motion. And the equation for period of a pendulum, period of a mass spring system, this is kind of interesting. It only depends on the mass at the end, how big is that block, and the stiffness or spring constant K. So it doesn't matter how long it is. And look, it doesn't even matter if you stretch this thing out 20 meters. That does not cause the period to get longer. This is a very, very strange concept. The farther you stretch it, wouldn't we expect that the farther you stretch it, the faster it takes, or the longer the period, maybe? Let's watch. Hang on. Let's try this out. I'm going to stop the thing by adding a bunch of friction. I need to just move this away. And I've got two identical springs here. 1 and 3, they are the same. Okay. What I'd like to do is pause the video. And we're going to take away that friction. 1, I'm going to pull really far down. 2, I'm going to pull not very far at all. It's the same mass. They have the same spring constant. Is their period the same? Let's watch. Look at that. They reached the bottom and the top at the same point. They're at the bottom. Now they're at the top. Now they're at the bottom. They actually complete a cycle in the exact same amount of time. It doesn't matter how far they get. That maximum distance from the center is totally irrelevant to their period. The only factors that matter for the period is the mass of the block, how big is it, and the stiffness or spring constant of that spring. The distance, the maximum distance, or we call it the maximum displacement, how far you get from the equilibrium, from the center line, is called the amplitude. Amplitude is the maximum distance, and we're going to actually say displacement, from the center line, or equilibrium, we call it. For a mass spring system, we measure the amplitude in meters. So you look at that dotted line, right, and you say, what's the farthest out you ever get? Maybe it's not this particular displacement. Maybe the block goes all the way out to here. Whatever the farthest is, that maximum displacement in meters, that's the amplitude. On to a pendulum. Here's the pendulum. It swings off to the left. Here's the middle. It swings off to the right. And we're going to get more precise, but what pulls the pendulum back in toward the middle? The answer is gravity. It's weight. And we're going to look at this more, but for now we'll just say gravity is the force that restores the pendulum back to equilibrium. That's why the pendulum executes simple harmonic motion. As soon as it swings off to one side, the gravity, the weight, pulls it right back in toward the middle, so it kind of swings back and forth. For a pendulum, we are going to express the amplitude as an angle. So if this full angle is 40, what's the amplitude? Well, you have to measure the amplitude from equilibrium. So the amplitude would be just 20. The period of a pendulum depends only on its length and on the acceleration due to gravity. So this is the length L. We know in general, period is the amount of time per oscillation. But there's a new concept we're going to use, frequency. It's the number of oscillations that occur per second, or per unit time. So if this thing is swinging back and forth like mad 10 times a second, the frequency would be 10. The unit for frequency is 1 over a second, and we call that a hertz. And we see there's a special relationship. Frequency and period are inverses.